Week 2, Lesson 3, Intermediate Columns and the Johnson Parabola. Lesson 1 classified the column. Lesson 2 loaded a long one with Euler. But Euler assumes the column stays elastic and shortened the slenderness and its predicted stress climbs until it would pass yield. In that middle zone, Euler overpredicts. Today we find the boundary and the formula that governs there, and close out the buckling arc. Here's the problem. A solid square steel column, 60 by 60 millimeters, pinned at both ends, 1.5 meters long, with a stated yield strength and the usual steel stiffness. Find the slenderness and the transition slenderness. Classify the column, then find its critical load with whichever formula governs, and show what Euler by itself would have claimed. The twist this lesson, you don't get to choose the formula until you compare. Concept 1. 3 regimes. A stocky column yields. Its strength sits at the yield plateau. A slender column buckles elastically. Euler governs, and the stress drops far below yield. Between them is the intermediate column, where yielding and buckling combine. Johnson's parabola starts at the yield plateau and curves down to meet the Euler curve tangentially at the transition. The whole reason it exists, in that middle zone, Euler would climb above yield, which can't happen. Concept 2. The transition slenderness. Slenderness is length over radius of gyration, plain L over R, no K. The transition, called the column stress determination factor, carries the stiffness, the yield strength, and the end condition factor under a radical. Then the rule is a single comparison. If the slenderness is at or below the transition, the column is intermediate and Johnson governs. Above it, the column is long and Euler governs. And notice the K lives inside the transition, not inside the slenderness. Concept 3. The Johnson parabola itself. The critical load is the area times a bracket, and the bracket is the yield strength minus a buckling penalty. Read it as full yield capacity, docked by a term that grows with slenderness. At zero slenderness, the penalty vanishes, and the bracket is pure yield. Push the slenderness up toward the transition, and the penalty grows until the parabola meets Euler. 3 things to transcribe exactly. It's yield minus the term. The whole slenderness fraction is squared, and the K² sits on top with the stiffness underneath. Setup, and the order is the lesson. You cannot pick a formula until you compare. First, get the section properties. It's a square, so both axes are identical, and there's no weak axis hunt. Then, compute the slenderness and the transition slenderness. Then compare and classify. Only then apply the matching formula. Note the yield strength is a stated given. It's grade dependent, while the stiffness is the same for every steel and comes from the handbook. Solve. Part 1. Properties, then classify. It's a square, so area is the side squared, and the 2 axes share the same inertia and radius of gyration. Slenderness is length over radius of gyration. The transition slenderness comes from the determination factor. Compare the 2. The slenderness sits below the transition, so this is an intermediate column. Johnson governs, Euler does not. Part 2. The Johnson load. Build the buckling penalty inside the bracket, subtract it from yield, and the bracket is the critical stress. Multiply by the area for the critical load, about 686 kilonewtons, and the sanity check that must always pass. The buckling stress lands below yield. Johnson delivered a stress under yield, exactly as an intermediate column should. Part 3. Why Euler is wrong here, the heart of the lesson. Apply Euler to the very same column, and it claims a buckling stress above yield. That's impossible. The column would have yielded first. Euler overpredicts across the whole intermediate zone, and that is exactly what the comparison against the transition slenderness protected us from. Johnson gives the real answer. Euler used blindly would have overshot the load by about 1/3. The answers: slenderness 87, transition 126, so the column is intermediate. Johnson gives a critical load of about 686 kilonewtons and a stress under yield. Euler, by contrast, would have claimed a stress above yield and is rejected. One comparison decided all of it. Classify first, and the right formula follows. Traps. 4 ways the intermediate column bites. 1. Using Euler without classifying. Always compare the slenderness to the transition first, because in this zone, Euler overpredicts. 2. Stuffing K into the slenderness. It's bare length over radius of gyration. The K belongs in the transition and the load, so don't double count it. 3. Botching the Johnson bracket. It's yield minus the penalty, and the whole slenderness fraction is squared, not just the slenderness. 4. Skipping the sanity check. The Johnson stress must come out below yield, and if it doesn't, you slipped. Quick recall. Slenderness is length over radius of gyration. The transition slenderness carries stiffness, yield, and the n factor under a radical. Johnson's load is the area times yield minus a squared buckling penalty. The rule: at or below the transition, it's intermediate, and Johnson governs. Above it, it's long, and Euler governs. Golden rule: compare before you compute, and the Johnson stress must land below yield. Next up, Lesson 4, Static Failure of Brittle Materials. That closes the column arc. Classify by slenderness, then Euler for a long column, and Johnson for an intermediate one. From here we leave buckling behind, and turn to static failure. How a part breaks under a steady load. Lesson 4 opens with brittle materials and the maximum normal stress theory, the first of the failure theories that run through the rest of machine design. Everything's at peprepengine.com. Cheat sheet, word solution, and a quiz attached here.